Our next speaker is Marc Weber. He's a PhD physicist and professor at the Washington State University with a specialty in positrons, of which there's kind of a whole chain of progress that he's made. And today we'll be talking about storage techniques.
Good morning, everybody. It's been a great honor to be here, and I've had a tremendous amount of fun both yesterday and on Tuesday. And I hope the fun continues for you as you go and listen to my talk. Anyway, so I want to talk about trapping charged particles because I did not want to say antimatter. I'm not quite there yet. But the main goal is to kind of put energy in a bottle that can be used wherever you need energy and where it's extremely difficult to resupply with fuel, meaning out in space, far away from any sun. Let's see. All right, so just briefly where I come from, I was told to say that every time. I do reside in Washington State, but contrary to Seattle on the west side, we are on the far eastern corner of Washington State in Pullman, in the area that's called the Palouse. If you ever had Windows operating system, you know what my area looks like, because that's one of the screensavers. Washington State University looks like that sometimes. Anyway, so this is about charged particles, and basically all the work is based on somebody else's work before me and with me. And I'm just one small grain in the machine of trying to get this to work. The main component or person is Kelvin Lin, who has all the fantastic ideas. I'm there to shoot the ideas down, and then he can come up with a new one. And then in between there are a number of people like Joe Jennings and Lloyd Pylan and many others along the way who've built things that I can shoot down again as well. Actually, the funding started right here in Huntsville. We got money from the Space Missile Defense Command initially, and then the Army Research Lab continued that. And the Keck Foundation was so kind to give us money to buy an old accelerator, which we tried to use to make positrons. All right, so this is like carrying owls to Athens, I feel. So I didn't really know who to talk to, so I made this as simple as possible, so I apologize if you fall asleep. That's my fault. Anyway, so I'll talk a little bit about antimatter, the way I use it in my everyday life for materials research, and then go on into applications for energy, and the three problems that I think circle around antimatter use for anything that involves energy. And then I'll talk about the experiment that I'm involved in to store charged particles, including positrons, and go on from there in the future. All right, antimatter, you all know this, so I'm just going to go quickly over this. We know every particle has its antiparticle. The electron has the positron, the proton has the antiproton, and so forth. They do annihilate each other mutually, as far as we know, even though there's the big mystery of why do we have more matter than antimatter. One of these questions to be resolved by maybe us. And we need to conserve energy momentum, and that's the main reason why we use antimatter in our everyday life. So, why do I work with positrons? Well, number one, it's a lot easier and cheaper to make positrons in a university lab where you have tens of thousands of dollars when you're lucky. You can buy a radioactive source that emits positrons, and then you can use them for your experiments. In comparison, Fermilab made a certain amount of antimatter, antiprotons. But all of those, this is the big thing of, the caveats. It takes a phenomenal amount of effort and time and energy with current technology and devices to make antimatter. But when I read and talk about you may have to build 1 million or 100 million telescopes in some far remote desert, this doesn't sound so bad anymore. Okay, and there are new methods where you can use high accelerator, electron accelerators to make positrons, and things become a lot easier just along with that concept. Okay, so my version of making antimatter, all the positrons come from radioactive decay of some isotope that lives for a certain amount of time. Our typical one in material science is sodium-22 that lives for 2.5 years. It's great for one mean graduate thesis lifetime. A faster way, if you want more positrons per time, then you need an isotope that decays more rapidly, so you have higher activity. And one of those is nitrogen-13 that you may or may not be familiar with that's used for PET scanners in positron emission tomography, as an example. The big thing that made positrons worthwhile in material science and also will make it worthwhile for energy storage concept is what's shown here, and that's called what we call moderation. Any generator of positrons these days produces positrons in a very, very broad range of energies. For beta decay, that's the beta decay energy spectrum. If you go to accelerators, you get something that goes even further out to higher energies. And these are log scales, and these are log scales. If you moderate them, and I'll go a little bit more into that, then you convert a small fraction of all these into one very low energy, narrow energy window. It's kind of like turning white light from a white light source into laser light. And then I can choose and pick how much I want to accelerate this or not. That moderation process is important if you want to get a beam and positrons and put them in a tank. You don't want MEV positrons to store in a tank where you have limited space and all the positrons will run into the wall very fast. So you want them low energy, confine them by some kind of confining force, including magnetic fields and electric fields. And the lower the energy of the positron, the lower the requirements on the fields to confine them. So moderation works by you shooting fast positrons from your source into a single crystal of tungsten, for example. The positrons will thermalize. A fraction will annihilate, and it's amazing, that's only about 10%. A large fraction will go right through, not so good. And then the remaining point something of a percent will come to the opposite side as nearly thermalized positrons. And then tungsten and a few other materials have the property that the work function for them is negative for the positron. So instead of like the electrons, they want to stay inside the material. Positrons want to roll out with a very small, very narrow energy window. And that is then ideal to accelerate and move positrons. The phase space is so nice that this by far surpasses what you get from electron sources with thermionic sources. So a positron microscope compared to an electron microscope is in principle a lot easier to build once you have the positrons. So in everyday life, just briefly, so to show you what my day job looks like, at least until recently, not this part, but that's where the money is in positrons, positron emission tomography, where you have a radioactive source that can give the outside observer an idea of where highly biologic activity goes on in a body, meaning cancer. My positron source looks more like this, and this is me like 20 years ago. That's called aging by positron. Anyway, I have a beam, and I'll show it maybe a little bit more later, but there's a source isotope here. They get moderated, and then they move down a magnetic guided positron beam in a vacuum system. And we look at things as vacancies in materials. We look at cracks, defect formation due to fatigue, anything that has to do with missing atoms. If you want to know about nothing, I can tell you about that. So here's more version of beam. One application is to measure how long a positron lives in a material. If there are fewer electrons around, it lives longer, and therefore you have a longer lifetime. So I can tell you by measuring the lifetime how big the open volume is. If there's one atom missing, two together in one die vacancy, and more. Or you can go to highly porous systems, and I can tell you the pore is 1 nanometer in size, roughly, half a nanometer, 2 nanometers. And that's very hard to do with any other technique that's out there. Or you look at the annihilation radiation, and energy momentum has to be conserved. So we have Doppler shifts in my little lab, and they tell me about the momentum of the electron in the system. So I know about the electronic environment near defects, near vacancies. And then again, I learn about vacancies, and I learn about property of materials. This would be zinc oxide. And this difference here means there's a certain concentration of vacancies in that material. OK, so much for that. Energy, and you know all this. But to me, this is the big shining thing that keeps me going, the carrot dangling in front of me, just barely out of reach. There's a huge amount of chemical energy stored in the tanks of any conventional rocket. And if you want to replace that just by energy with antimatter, those tons or trillions or no, what is it, terajoules of energy are confined in less than a gram of antimatter. That's the carrot. This is another part of the carrot. If you wanted to go to space, and this is my non-specialist, non-rocket scientist, I'm just a simple physicist version of rocket science, you have two choices. You can make the material out of the exhaust of your rocket go faster, we're limited by chemistry, how fast things can burn. Or you can lose more of your initial mass to throw out the back and have a little bit less left over to deliver a payload somewhere. And then I just took examples of real-day life. This is basically chemical fuel burning. If you use ions, you can go a little faster. If you use photons, obviously you get the highest velocity coming out, but the lowest momentum of transfer. Any one of these methods, you need more and more energy. And I don't think it would be a good idea to just throw antimatter out up front before we know how to do it, at least in principle. So there are three problems with storing with using antimatter in our life for energy. I call them the 3 C's because I was forbidden to say problems. Me as a German, I like to call problems. Americans like to call them opportunities. So my compromise is to call them challenges. So the first one is, of course, creation, and I'll skip that one because I guess the next speaker will be much more knowledgeable about that than I am. The one I'm concerned with is conversion. Conversion is the one where you just use antimatter annihilation to do something that gives you either higher velocity, so delta V, or you power your astronauts in space to keep them entertained for 20 years. Video games is probably not good enough for that. Anyway, and the big problem that I think needs to be solved first is confining antimatter. If you don't know how to confine them for decades, there's no point making more. If you don't know how to confine them, there's no point of burning it up to make a spaceship go faster. So this is the conventional way, and I'm not the expert. The expert is at University of San Diego in California, Cliff Circo. He's perfected the scheme so far that at CERN they're now able to make anti-hydrogen atoms in quite significant numbers to do atomic physics, one of my previous careers. Not at CERN, but atomic physics. Anyway, so you have a cylinder. These are my drawing skills. You have a magnetic field that is supposed to be homogenic and very parallel, aligned with the cylinder. And then at each end of the cylinder, you have an electric barrier. So once you have charged particles inside there, they will be confined radially by the magnetic field to some extent, and they will be confined axially by the retarding potential at each end. So in principle, a positron bounces around in here forever, but the slightest imperfections will give it a kick radially and move outwards. The only thing that keeps lots of positrons confined radially is the combined angular momentum of this cloud of plasma of charged particles. And then you come up with ideas that it's just basically a rigid system that rotates in the magnetic field. And angular momentum forbids it from expanding outwards. But any imperfections on the wall could cause trouble and gradual drift outwards. So that's the simple part, and that's been driven to about 10 to 9 positrons a billion. That's a far cry from usable. A gram would be 1 billion times this and 1 billion times that. The next problem is the big one, in my mind. You're putting 1 billion positrons in there. They all have the same charge. They all repel each other. They all push against the end caps. They will eventually also push against the magnetic field, but that barrier, the Brion limit, is way higher than the electric field end cap requirement. So the 1 billion positrons in a tube that's the size of roughly a cubic meter would cost you about a kilovolt of bias at each end. To maintain that, you need a power supply, and that probably consumes more energy than it's stored in those 1 billion positrons. This is not the way to go, because you can't squeeze any further than this. And very rapidly, you end up at hundreds of kilovolts to confine particles this way. And this will work whether you want to store positrons or electrons. So the cheap, easy way is to try to store electrons rather than positrons. That's what we try first, and then we'll try positrons next. So this is just a repeating of the problem. You have a magnetic field that keeps positrons on a line, or electrons, but they repel each other. So how do you keep that from happening? Well, in principle, real life nature has the solution for this. It's called a metal. You have a lot of electrons confined into a small volume by a lot of protons, and the charge equals and balances, and you shield each other so there's no explosion. So what we need to do is separate those two charged particles by putting a metallic mirror in between. And then the charged particle on one side of the mirror will be shielded from the one behind the mirror. We call that Faraday cage or electrostatic mirrors. So if you drive this to fit your circular environment or cylindrical environment, you just have a stack of tubes, like soda straws in a bundle, and each of those soda straws has a metal wall. And you make these straws really long to basically replace the volume of the single large trap with thousands and thousands of very small traps. So that's what we tried. How do you make the tubes? So we thought, okay, let's start with 100 micrometer diameter tubes and make them all 100 millimeter long. And then they're stacked together to basically form the size of a soda can. We used to say Coke can, but somebody said, you can't do that. So we now think we can make a soda can out of these wafers. And you have, of course, to align all these holes in each wafer with the holes of the next wafer and so forth. So that's basically you trying to do use a hole punch to go through a few papers and then make an inch-thick stack out of those. And it's not so easy. So the techniques that are available, at least in our area, Intel and others, is called microelectromechanical machining, including deep reactive ion etching, DRI, and other techniques permit you to make a mask and basically put holes to a single silicon wafer. Then we take 13 or 14 of those and stack them together and have them coated with gold. So that's our metallic wall. And then that'll be okay. If you take cross sections, this is the wafer we have, and it's about this size. And we have like 20 of them now, or stacks. Cut through, you can barely see the holes, and you zoom in with electron microscopy. The big issues are to make these two holes go straight and the same diameter all across and have no rounded edges at the corners and any of these things that happen when you do etching. So we tried for quite a long time to do this ourselves, but eventually we said, okay, there are companies that can do this better, and we bought the wafers and we stack and coat them ourselves. And now what you want to do is, instead of having one single trap where you stack more and more particles in them in powers of 10, you have to compensate the charge, the space charge, with higher and higher potentials at the end. You basically make one little one, and you put on the order of 1 million to 100 million electrons or positrons into each tube, and then you make more parallel tubes rather than filling the same one higher and higher density. So now your confining potential is on the order of 10 volt. The proverbial 9-volt battery will suffice. And that'll last a little bit longer. So that's what we built, or had made. Here's our stack. Each one of these is the little wafer stack that I showed before. We have about 10 or so on them in a row. There are bigger wafers in between which have oxide coating for insulation, so we can play around with this trap and do science experiments, or what we have fun, as I call it. Here's the trap in the bigger system, and this whole thing then slides into a 7 Tesla superconducting magnet. That's this thing here. That's about as tall as I am, and about this diameter. So this is not space-worthy yet at all. And then you need to find a way to fill this. So we have, back here in the corner is the back end of a Van de Graaff accelerator that was intended to make positrons, and it hasn't made positrons. The moderation process didn't work so well yet, so we need to work on that. But then you have the magnetic guiding of charged particles to the superconducting magnet. And then you have the problem of getting low field environment electrons or positrons into a high magnetic field. That's called a magnetic bottleneck, except that ours works the wrong way. We need to get them in through the bottleneck. So we need to put the ship into the bottle first. And then we do our trap experiments, and then out come whatever is left over at the end. So that's the setup. And this is a test bed. You can build a variety of traps, different hole geometries, different size of traps. And we can basically install them in here and do whatever you want to do, as long as it fits in the system and is non-magnetic. I mean, it's amazing how much stuff in the silicon business ends up with a metal that's magnetic, and we can't use in here in 7 Tesla. So this is the simple. Again, I use the bad words. I call this a trash compacting technology, and I'm told that's not a good word either. Anyway, So the entrance barrier you lower and you let your beam of particles in, and then you raise the entrance barrier. You can do this more sophisticated, like the San Diego group does. You can do a pulse beam, but for all practical purposes, you don't lose much more by doing just on and off and let something go in, and whatever happens to be in here will confine. So now there's this cloud of charge in there. That's not enough. That's just 1, 2. So ideally, you squeeze the confining potential over to the side, you compact the existing charge, and you make room for the next batch of charge. You have those, and then you repeat this until you have a sufficient number of charges in there. You wait for some time that you think is useful, and then you let the particles out and see what happens and how many you have left over. And that's your basic how well does this trap work idea. So anyway, so you do these experiments, and my results are very encouraging and not so encouraging. So there's good news, bad news, and I think, as I heard yesterday, mostly bad news. So transmission works, except there are a bunch of holes. These are all 100 micrometer holes, and we just guide the beam through a different hole and see how much comes through. And then you get some that are black, which is something, dirt or whatever. This is kind of how many holes transmit how much. And then we say, okay, you want a trap, and this is a 1 millisecond, not 1 mega year or 1 anything. It's a millisecond. And I have illuminated about 10 holes with my source of electrons, squeezed down into the higher magnetic field. And then you can say, well, let's trap 10 milliseconds, but only look at the cases where you have more than 1 hole with charge left over after your time. So these are 4 holes in parallel showing charge coming out after 10 milliseconds. So this is kind of a step 1. Can you fill multiple holes in parallel and have something come out afterwards? If that doesn't work, let's go home and do something else. Well, that worked, so I got to continue. So the other thing was, well, how long does it take for these 2, 3 EV electrons that go in to just bounce around in there and lose energy as they bounce back and forth? And that seemed to take on the order of a few microseconds. So here what I do is I measure how fast they are coming out of the trap in 1 dimension, but overall. So as they come in, they still have, after a short time, this was 1 microsecond, they still have basically initial kinetic energy. After 3 microseconds, they had a significant fraction with much lower energy. So the trapping somehow makes them interact with the walls and the system and the bouncing, and they can lose energy parallel to my beam system. Then the more important thing is, well, how long will they stay? So here I fill as long as I hold the charge inside. Number 1, I can have more in my traps as I fill longer, which doesn't make sense when you just have the beam system open. To fill in a beam, they bounce right back out, but some are more stay inside. Something I need to learn how to do that better. But after 1 second, I lose signal to noise, though I can't see anything left anymore afterwards. So we've tried this for a couple of years now. I've tried to vary the intensity of the electron beam going in, but overall, the trap lives for about 45 milliseconds. Okay. And so far, I haven't been able to come up with more, and the typical answer then is your alignment is not perfect. We do know that we have multiple particles, at least at short times, in each trap, because the signal is higher. But the alignment we're working on is we have a piezo control system that gives us a few milliradians, which is pretty tight for us, but not for astrophysics. But it matters. And just bring up again, he has to come up with new ideas. I will break him in my experiment. And some people will build them in between. I was going to talk more about how to make positrons, but I'll leave that to another talk. Thank you.
Okay, Marc, it's Greg Matloff again, and this is a physics question,
Okay.
and it relates to the EM drive and things like that, and questions about conservation of linear momentum.
Okay.
Imagine that you have an electron that is constrained to stand still.
Yeah.
A positron is speeding towards it with
Yeah.
a certain linear momentum. They interact, annihilate, and a gamma ray is given off. Are we sure, 2 gamma rays, are we sure that the linear momentum from the 2 gamma rays together will be the same as the linear momentum of the original moving particle?
Actually, we have done that experiment.
Yeah.
In our lab, we call that annihilation in flight. And it happens sometimes. Typically, they whiz past each other and nothing much more than elastic collisions or inelastic collisions happen, but no annihilation. But in a small number of cases. So this spectrum is basically color-coded. How many events per second do I get? On the right side is the difference in energy between the two photons. So that relates to the Doppler shift that you share among the photons. One gets a little blue shift, the other one has to get red shifted in my lab. The energy up is the sum of both photons together. So this horizontal line is 1 MeV, the rest mass of those two particles. And then upwards here is the kinetic energy on top of that from the positron as it comes in. I happen to be running about 70 keV, and you can see the slight enhanced bridge here. That is due to 70 keV positrons reaching a sample of, I don't remember what it was now, but silicon, let's say. And the electrons inside there, the conduction band electrons and the valence band electrons annihilate with positrons to a very small fraction, and that's what you get then. That is the two photons coming out, not quite anti-parallel, but somewhat forward.
Momentum is conserved.
Yes.
Okay, thank you.
As far as I can tell with this.
Very good.
Hey, Mark. Grover Swartzlander, Rochester Institute of Technology. Just a simple question. Advantages and disadvantages of storing anti-hydrogen versus anti-protons?
Okay, this is my positron version of it, so I'm biased. But for me, it's much harder to see anti-protons being made. I mean, CERN is working at it very hard, and as far as I know, that's pretty much the only place in the world where you can get anti-protons. Positrons, you can buy a radioactive source, and you get a certain amount per time. You can take electrons, accelerate them to a few MeV. 10 MeV is probably the highest cross-section. And you make pair creation from Bremsstrahlung, and then you have your positrons. And that's a fairly well-understood process. For example, Jefferson Lab, they want to build an intense beam of positrons by just slamming very high-energy electrons, polarized, into a liquid target, and then you have to deal with the heat, but you will get pair creation and positrons, and even polarized positrons out of it. Not that that matters here right now, but it does matter to some. Okay?
Next speaker, please. Thank you.
All right.